we'll continue with Ramsey. Let me rephrase the main Ramsey theorem in a slightly stupid way. So the simple finite Ramsey theorem said that for every kr, there exists a kn such that, right, so for every r, there's an n such that the complete graph on n vertices, no matter how we edge color it with two colors, has a monochromatic kr in it with respect to that coloring. The reason I'm rephrasing it like this is that I want to look at what happens if we replace either of these two complete graphs with an arbitrary graph, H or G, today, and then see how the problem changes and what else one can look at or say or whatever. So let's generalize this kr to an arbitrary graph H. So is it still true that for every finite graph H, there's an n such that Kn, no matter how we edge color it with two colors, contains a monochromatic H? Yes, of course it's true, because just consider Kr for R the order of H, and then we'll find a monochromatic Kr in that, Kn, if n is chosen big enough, and inside that Kr, we'll find a copy of Rh, because R was chosen big enough, namely as the order of H. Okay, so that's not going to lead anywhere interesting, but if we focus on this n that is needed, then the problem changes. So let me put these up there. This n, the smallest such n, is called the Ramsey number of little r. Right, for every r, there are some n, all big enough n will do, and we're interested in the smallest n such that no matter how we edge color Kn, there's going to be a monochromatic Kr. Right? And the smallest such n is called the Ramsey number of R. And in the same way, we can now look at the Ramsey number of H. And if H is a lot sparser than Kr, has fewer edges, maybe on little r vertices, it could happen that we can make do with a smaller n. Right, so that is a very reasonable question. This Ramsey number of H might be smaller than the Ramsey number of the order of H. And similarly, we can, or slightly more generally, we can look at two graphs, H1 and H2, where we want a green copy of H1 or a red copy of H2 in any red-green edge coloring of Kn. Right, it's important that we make up our minds which is which. So we're not just asking where we want for a monochromatic H1 or a monochromatic H2. You can ask that too, but that's not what we're doing now. So we're asking for n big enough such that every red-green edge coloring of Kn yields a green H1 or a red H2. Or in the earlier terminology, before I introduced coloring to Ramsey problems, we used to say that if G has big enough order, then either G itself or its complement contains a Kr, right? And in this same terminology now, we can ask which order G must have so that H will contain a copy of H1, or its complement will contain a copy of H2. And in fact, we're asking whether making G big enough will ensure that. Right? But we know that from Ramsey's theorem that this will happen, but we're asking for the smallest order of a graph G where this will happen. Okay. So, before I'll give you one little theorem of this type, which is particularly simple and particularly neat. Just let me draw your attention to the fact that if we prove that the Ramsey number is equal to something, or at most or at least something, then these proofs have very different flavor. So a proof of, how should we start? When we want to show that the Ramsey number is at most something, then what do? We'll take a Kn that is as big as we claim there will be enough, and then our adversary will be allowed to two-color the edges of that Kn, and we'll have to adapt to whatever evil scheme our adversary comes up with by finding, for example, a green H1 or a red H2 with respect to that coloring, which we cannot choose. Right? So proofs of a Ramsey number being at most something amount to being able to deal with the intricacies of a graph G that our adversary comes up with, or a two-edge coloring of Kn that the adversary comes up with, and adapt to these intricacies by flexibly finding either H1 green or H2 red, or a copy of H in either color. So we have to adapt to some cover to some structure that's given to us, and for proofs that the Ramsey number is at least something, we are the adversary. So we can say, okay, we prove that whoever claims that something is a Ramsey graph has this property, we can make their life harder by constructing a graph that is slightly smaller than this, and that doesn't have a green H1 or a red H2, or a monochromatic H, or a monochromatic Kr. Right? So we do the constructing. We construct a G that may be complicated, but we have to come up with a complication. We can invent it. And we construct it in such a devious way, if you want to stay in the image, that it itself doesn't contain H1 and its complement doesn't contain H2. But we're allowed to do the constructing. So these are very different kinds of proof flavors. Okay. I think that's all I wanted to say in general. No, there's one more thing. Sometimes construction proofs in graph theory can be replaced by a random argument. We'll be getting to random graphs the week after next, but the existence of a particular graph with a particular property in the classical scenario is proved by constructing such an animal. But in random graphs, one can prove the existence of graphs with certain properties simply by showing that in a suitable probability space, the probability that such a graph has this property is bigger than 0. And then maybe one still doesn't know what these graphs might look like, but one knows they exist. So a particularly deviously colored, edge-colored Kn, or a particularly carefully and mischievously constructed G that doesn't conform to this, where G doesn't contain H1 and the complement doesn't contain H2. This existence might come not out of a construction, but out of an argument that shows that such things must exist because the probability of a random G having that property is bigger than 0. We'll get there, and we'll prove a lower bound for the classical Ramsey number R of little r in exactly this way, as the first little application of random graphs in the week after next. Okay, so that really is all I wanted to say in general. Now, let me give you the first little proposition. That's 291, 921. And that says that for every s and every t integers, at least 1, and for every tree t of order t, the Ramsey number of t and ks, so this thing here, h1 is our given tree, and h2 is ks with this s, is equal to s minus 1 times t minus 1 plus 1. And that is one of these very, very rare theorems, elementary theorems, and they're only elementary theorems where equality is known, where the two bounds are sharp, right? And it is also remarkable that this depends only on the order of t, of the tree. It doesn't depend on the structure of the tree. So for all trees of the same order, that's the same bound. So that is quite interesting, and, well, the proof is easy. Let's do the construction first. So we want to show that we need at least this many vertices in G, so that G contains a copy of T, or the complement contains a copy of Ks, so G contains T or has S independent vertices. Right, we want to show that we need at least this many vertices on a graph G. How do we do it? By constructing a G that has fewer than this number of vertices, namely this many, just below, that doesn't contain T and doesn't have S independent vertices. Yeah, and that's not so hard. So how can we make sure that G, the graph we're constructing, doesn't contain T itself? Well, one way to ensure that is by making the components of G too small. Right, if G is disconnected and the components don't have enough vertices for T to live in a component, then T can't live in the whole graph either, because T is connected. I mean, that's a very, very crude argument. But it's one way of ensuring that G doesn't contain T. And if we go along that path, how can we at the same time ensure that G doesn't have S independent vertices? Well, we can certainly find an independent set if we pick a vertex from each component, so we better have at most s minus 1 components. And is that good enough if we have only s minus 1 components? Well, no. If there's a non-edge in even one of those components, we still have s independent vertices. Right? But there's no need to allow that, because if the components are small enough, no matter what edges they have, they can't contain T. So we make these components complete. And take s minus 1 component. So what is the whole graph? The whole graph is the complement of this. Right, and that has exactly this number of vertices, and that's it. Yeah. Questions? Okay, so that was easy. Let's prove the other direction. Now, we want to show that if we do have one more vertex, then no matter how G is structured, we can find a copy of T in it unless we have S independent vertices. Okay, so how does one even think about that? I have no idea what G is, other than that it's big. We must somehow play these two things out against each other. That assuming we don't have T, then how many independent vertices might that force, or vice versa. We'll do it vice versa. So suppose we don't have S independent vertices. What can we say? Well, if G has no set of S independent vertices, then think of coloring. Then in any proper coloring now, in the sense of the chromatic chapter, the color classes must be small, because color classes are independent. Then we need many classes. If the color classes are small, we need many classes. So then the chromatic number is big. How big? Well, the color classes have size at most S minus 1. So n is the order of G divided by S minus 1. Right, and we can even say, well, since the chromatic number is an integer, we can even round up. And now, this little one has its big day, because if we take this, then we get to T minus 1 if S minus 1 divides n, but it doesn't divide n because of that. So we get one more. This is not T minus 1, but T. Aha. So the chromatic number of G is at least, or is T. But then G has a critically T-chromatic subgraph whose min degree is big. Right, remember that from the coloring chapter? So if you have a graph that needs t colors, and you make it minimal, critical, with needing t colors by deleting vertices until it's about to lose that property if you delete another vertex. So you still need t colors. Then call this graph H. The min degree of H must be at least t minus 1, because if it had a vertex of degree t minus 2, we could delete that vertex, use criticality to deduce that after deleting that vertex, we can color with t minus 1 colors, and then put the vertex back. And since it has only t minus 2 neighbors, we can color it with the remaining one of the t minus 1 colors, and we'd have a contradiction to the chromatic number of H still being t. Okay, so there is this subgraph of G that has min degree at least t minus 1. And then I write clearly, and I'll show you why it's clear. This H contains a copy of T. And that's easy. We just embed T. T has little t vertices, right? We just embed that vertex by vertex, always keeping the embedded part connected. So we're growing our tree T, this T vertex by vertex, always keeping the initial segments connected, and then we want to add another vertex. This next vertex we want to embed has only one neighbor in T amongst the vertices of T we've already embedded. This vertex here has at most in G, at most how many neighbors? Well, if we haven't embedded all of T, then this isn't all of T. So this is only t minus 1 vertices at most. Then the neighbors in here are at most t minus 2. So if this vertex, I'm now talking about the image, if this vertex has degree at least t minus 1, then we can find it a new neighbor in the image where we want to embed T, i.e. in the graph H. So we can inductively embed T, and that's what we wanted. Yeah. So that's a little more substantial than that. And it's sort of quite nice that we need the sort of things that we had earlier as observations that we just picked up and then didn't elaborate much on, like critically T-chromatic graphs and this embeddability. Yeah. Okay, questions? Okay. Right, so now let me wipe the board. So next, we want to look at what happens if we replace the second complete graph, this one here, with an arbitrary graph. I'm not calling that H, I'm calling that G now. So does that become a sensible question? Well, no. If we're just asking for the existence, then we might choose G to be Kn, so that makes no sense just yet. But we might ask for a minimal graph G, whose two edge colorings still yield monochromatic copies of, for example, KR or any H. So, definition, call G star Ramsey minimal for H if every true edge coloring of G star yields a monochromatic copy of H. And G star is minimal with this property. Right, so if we take any proper subgraph of G star, then it loses that property. If we delete a vertex or an edge, then there exists a true edge coloring of that smaller graph than G star without a monochromatic copy of H. Okay, so yeah, how much does that change the problem? Well, do such things exist? Yes, of course they exist. Kn has the property, every true edge coloring of Kn, when n is the Ramsey number of H, yields a monochromatic copy of H. So we can just make it minimal if it isn't. Can we delete a vertex? No, we can't delete a vertex because then if that still had the property, then that would contradict the definition of the Ramsey number of H of this Kn realizing that Ramsey number, right? Because any two edge coloring of Kn minus 1, which would then contain this minimal G star, which we found by inside Kn by deleting a vertex and maybe some edges, that would still that would induce a true edge coloring of this G star, and if that G star then contained a monochromatic H, then so would the Kn minus 1 by virtue of containing G star. So we can't delete a vertex, but we might delete edges. So if Kn isn't minimal, we might delete some edges, and then we would eventually get to some minimal G star inside the Kn. That has this property. Okay, question? Do we always get to the same G star? Is it unique? Right, if we start with the Ramsey number with Kn, with n the Ramsey number of H, and delete edges until we're minimal with the property that every true edge coloring of the graph G star that remains yields a monochromatic copy of H. Are all these graphs G star that we get to isomorphic? Hard to say. Well, we're going to prove that they're not unique. In fact, we're going to prove that there are infinitely many. It depends a little bit on H. I mean, if H is a K1, then they're not infinitely many, but so that's proposition. 923. For every tree, is that how I want to start? Yeah. Every tree T, that's not a star. There are infinitely many Ramsey minimal graphs. So in particular, they can't all be found by starting with Kn and then throwing away edges, because we only get to finitely many there. In particular, they're not unique. If we can't, yeah, they're not at all unique. There are infinitely many of those. Okay. So if we follow this rough idea of starting with some graph, some large graph that has this property, that every two edge coloring yields a monochromatic edge, and then make it minimal somehow, we want to ensure that the minimal graph we get to is still large. If we want to get to infinitely many, potentially, then those we get to will be arbitrarily large. So we must somehow, for any given order, find a starting graph G such that if we make that minimal, maybe in a clever way, that inside that G, the G star that we find, that is Ramsey minimal for H, is big. And it's not enough to start with G big, because G could, for example, be a Kn with n unnecessarily large. And in that huge Kn, we'd first find a small Kn, namely the Ramsey number and the Ramsey number of H. And then inside there, we could only delete edges, and then we'd only get to finitely many. Right? So either we have to do the minimization in a clever way, or we have to start with cleverly chosen G's that are cleverly chosen in the sense that no matter how we do the minimization, we get to different G stars, arbitrarily large G stars. And neither is obviously the better strategy. It's the latter strategy that's going to work. But here's the very, very pretty way to do that. So for want of any sort of obvious idea of how to go about it, let's just look at any properties we might glean from the unknown G star. So properties, what can we say about properties of these Ramsey minimal graphs G star for a given tree T? There's one thing we can say. So G star can't be a tree or a forest. Why? Because you can two-edge color any tree by coloring the distance classes alternately. So pick a vertex, color all the incident edges green, color all the uncolored edges incident with the neighbors red, color all the edges incident with those and that don't have a color yet green, and keep doing that. So that's a proper two-edge coloring of any tree or forest. Do it in every component. that will not have a monochromatic H as long as H is a tree that is not a star. Right, so when these are all red, and those are going to be red too, and inside we have green, and then the next one is green again, and so on. So this can't contain a green tree T unless T is a star, right? There is no path of length 3. But if T is a tree that is not a star, it has a path of length 3. So G star, no matter how we find it, somehow automatically in some big enough G or whatever, is not going to be a forest. So G star has a cycle. Contains a cycle. Idea, force R to be big. If we can make this cycle as large as we like, then we get infinitely many G stars. Well, clear, if we have found one G star, choose the next little r, one bigger than the entire set of vertices of the G star we just found. So if we can make this cycle long, right, so how can we force a long cycle? Well, what we know is there exists some cycle, and we can force that to be long by ensuring that there are no small cycles. So, force the girth of G to be bigger than R. That's enough. But then, if we can find G that has this Ramsey property for H, that has girth at least R, then we can make it minimal by deleting whatever vertices or edges or something. We're not going to introduce a short cycle by deleting stuff. So whichever G star we get to inside a graph G, of girth at least R, will either be a forest or it will still have girth, well, it will have girth at least R. And it must contain a cycle, so it will contain this long cycle that we wanted to. So all we need is to start with a G that has the desired property, namely for every true edge coloring of G, there's a monochromatic H, T, that has large girth. But that smacks of something, which you will no doubt have smelt already. Yeah, the Erdős theorem. Also going to be proved in the week after next. Right, so Erdős's theorem says that there are graphs of large girth and large chromatic number. You could wish for values of both these as large as you like, and there will exist a graph that has chromatic number and girth at least that. Okay, so all that remains to be done is to see whether we can find a G that does that with this large chromatic number. Okay, so what chromatic number might force a green or a red T? Right? If we can find a chromatic number that forces that, then choosing our graph G, a graph G with that chromatic number and large girth, find inside that G a G star that will still have large girth, and then we'll be done. So we're looking for a chromatic number that will force on any edge coloring of the graph a copy of T. Okay. So to force in some graph G, so G is any big graph, it will later have girth at least R, to force in G a green, okay, edge-colored green-red, a green T, it suffices to have what? As we just saw in the earlier argument, large min degree. So if the min degree is the order of T even minus 1, if the min degree is at least order T minus 1, then we can find a copy of T. So it suffices to have green epsilon to be at least T. That's the order of T. In fact, T minus 1 would do. Right? So we take a graph G, and we're edge coloring it red-green. And if it so happens that the number of green edges divided by the number of vertices is at least T, then on the green edges alone, we can find a subgraph of min degree at least T, and that will contain a green tree T, right, by this choice. And the same for red. So to force a monochromatic, it suffices to have epsilon of G at least 2T. Yeah. And that's why I'm working with epsilon here rather than chromatic number or min degree or something, because the epsilon does not neatly add up. The green and the red epsilon together make the overall epsilon, right? Because that's just the number of edges, and the edges are green or red, divided by the same number of vertices. Okay, so we should get a monochromatic T if epsilon of G is at least 2T. Okay. So start with G prime of chromatic number bigger than 2t, 4t. 4t. Right, that will have a critically that chromatic subgraph of min degree and therefore average degree at least 4t, and therefore the epsilon will be at least 2t. So once more, start with a large chromatic number, find inside a subgraph that has min degree the same minus 1. Min degree is certainly at least the average degree. Average degree is twice epsilon. So if we start with 4t, then we'll get this. Yeah, and girth of G prime to be at least R. End of proof.